ever stop to think about how we actually quantify uncertainty in life? Things like,
Mm.
how does a life insurance company figure out the odds of someone surviving another year?
Or how public health officials try to model the chance of big health changes across the whole population over time.
Exactly. It sounds incredibly complex, almost impossible maybe, to pin a precise number on things that feel so, well, uncertain.
It does seem that way.
But today we're doing a deep dive into the basic mathematical models that actually let us do just that.
Right. Our mission, really, is to unpack the core ideas behind two key models, the Two-State Markov Model and the Poisson Model.
Okay.
And these aren't just, abstract equations floating around. They're really powerful tools, especially in fields like actuarial science. They help us analyze how things move between different states, the classic example being alive and dead, and crucially, they let us estimate the underlying rates of these changes, often with surprising accuracy.
And we're grounding this discussion in some core actuarial education materials, right, to give us a solid structure.
Exactly. These materials give us a really clear look at how these models are built, how they're used in the real world, and, importantly, the critical assumptions they rely on.
Assumptions are key here, I imagine.
Oh, definitely.
So get ready, everyone. You're about to get a pretty thorough, practical understanding of some actually really fascinating statistical foundations.
Let's start with the first one, the Two-State Markov Model. It's a surprisingly elegant way to think about life in transitions.
Okay.
At its heart, it's looking at a random process where something, let's just call it a life for simplicity, moves from one state to another.
And the simplest version just has two states.
That's right. The most basic version, and the one we'll focus on, tracks a life moving from an alive state to a dead state.
Just one direction.
One direction.
Yeah.
And this simple model, yes, alive to dead. And what drives this movement, what governs it, is something called a transition intensity.
Transition intensity. Okay.
Yeah, it's usually written as E, often with a subscript like X plus T, indicating age and time. You can think of it as the sort of instantaneous force or pull moving someone from the alive state to the dead state at a specific age and time.
So a higher intensity means a stronger pull, a quicker transition is more likely.
Precisely. A higher intensity means the risk is higher at that instant.
Okay, so with this intensity concept, we can then define some key probabilities, I guess.
Exactly. First, there's one denoted TQX.
TQX, what do the letters mean?
So the T is the time period we're looking at, often in years. The Q stands for the probability of, well, quitting the alive state or dying. And X is the starting age.
Got it.
So TQX is just the probability that a person who is currently age X will enter that dead state sometime within the next T years.
Makes sense. And the flip side, staying alive.
That's TPX. Here, P stands for persisting or surviving.
Oh, okay.
So TPX is the probability that someone aged X right now will remain in the alive state. They'll survive for the entire next T years.
Right. And these two, TPX and TQX, they must add up to 1, right? You either survive the period or you don't.
Over that specific period, TTP, yes, assuming those are the only two possibilities. They're fundamental building blocks for, well, everything from pricing life insurance to planning for pensions or even forecasting healthcare needs.
Okay, this is where you mentioned it gets really interesting, the assumptions behind these models. For them to work, they need some simplifications.
They absolutely do. And the first one is a big one. It's called the Markov assumption.
The Markov assumption. That sounds significant. What does it mean in practical terms? Does it mean the model ignores important things about a person's history, like their health over their whole life?
That's a really sharp question because, yes, that's exactly what it means fundamentally. The Markov assumption states that the chance of future events like dying depends only on the state you're in right now, alive or dead, and your current age.
Only the present.
Only the present state and age. It explicitly does not depend on your past history. So things like whether you had a serious illness 5 years ago, or your job, or your lifestyle habits up to this point. The basic model doesn't look at those.
Wow, okay. That does sound like a massive simplification of reality.
It is, but it's crucial for making the mathematics tractable. And as the source material points out, if we did have detailed information on those past factors,
You'd use a different model.
you'd either build more specific models for different groups, or you might incorporate those factors using something like a regression model. But for this foundational two-state framework, the Markov property makes things memoryless. The past is forgotten, mathematically speaking.
Memoryless, okay. So if the past doesn't matter in the model, what about that transition intensity itself? How does that link to probability over, say, a really short time?
That brings us to the second assumption. It basically clarifies how that intensity translates into a probability over a tiny, tiny interval of time. Let's call it dt.
Like an instant.
Almost, yeah. The probability of dying within that infinitesimally small time dt is assumed to be simply the intensity at that moment, multiplied by the length of the time interval dt. So t times dt.
Okay, so intensity times duration gives probability for a tiny slice of time.
Exactly. It connects the continuous rate intensity to a discrete probability for a very short period.
And there was a third assumption.
Yes. The third one often simplifies calculations even more. It assumes that this force of mortality is actually constant over a short period. A common simplification is to assume it's constant for a whole year, like between exact age x and exact age x plus 1.
Constant for a whole year, but surely the risk of dying changes as you get older, even within a year.
You're absolutely right, it does. In reality, mortality intensity isn't perfectly constant, so this is a simplification, mainly for mathematical convenience in many applications. It makes the integrals much easier to solve.
Right.
It's worth remembering, though, this whole setup, the two states, the transitions, it's an example of what's called a Markov jump process. And while we're focused on the simple alive-dead model, you can generalize this.
How so?
You could have multi-state models. Imagine tracking transitions between healthy, sick, and dead, or different levels of disability. The core ideas extend.
Okay, that makes sense. So we have the states, the probabilities like TQX and TPX, and these simplifying assumptions like Markov and constant intensity. How does the math actually let us quantify the survival probability, the TPX?
Okay, so the main formula for the survival probability, TPX, comes directly from that transition intensity. It involves calculus specifically, an integral.
Oh, okay. Lay it on me.
The formula is TPX equals XP. That's the exponential function, e to the power of.
Right.
You have the power of the negative integral from time 0 up to time t of the force of mortality at age x plus integrated with respect to s. So TPX equals XXP.
Wow, okay. So that integral is essentially summing up the risk, the me, over the whole time period, t.
That's a great way to think about it, yeah. It accumulates all those tiny instantaneous risks of death over the entire duration you're interested in. The exponential function then converts that accumulated risk into a survival probability.
And how does that formula change if we use the simplification we talked about, the constant force of mortality?
Well, that's where things get really neat and much simpler. If we assume p is constant over the period 0 to t.
Like that third assumption.
Exactly. If p is constant, that integral just becomes tp. So the formula simplifies dramatically to tpx equals e.
E to the minus mut-t, that's much cleaner.
It is. And this result, pbxes e under constant source of mortality, is super important. It pops up all over actuarial science. It comes directly from those assumptions and relates to some deeper mathematical structures called Kolmogorov forward equations, though we don't need to dive deep into those today.
Okay, but why is getting to this formula so significant? Why does this specific derivation matter?
Because these derivations, from the intensity to the integral form, and then to the simplified exponential form, they provide the solid mathematical foundation. They show us how to calculate survival probabilities from the underlying mortality rates or forces.
It connects the theory to the calculation.
Precisely. It's what allowed actuaries, historically, to move from just observing deaths to actually building predictive models and, pricing things like life insurance. It turns the abstract idea of risk into something you can actually quantify and work with financially.
That's really cool. Okay, so we have these elegant models. But how do we actually, connect them to the real world? How do we get the value for the force of mortality from actual data?
Right. Bridging that gap is crucial. We start by collecting observations. You typically observe a group of individuals, let's say N people, over a specific time frame.
Okay.
Then for each individual E in your study, you record some key information. First, you need an indicator. Let's call it day. It's simple. Day is 1 if that person dies during your observation period, and it's 0 if they survive the whole period.
So just tracking the deaths?
Tracking the outcome, yes. But you also need something else, which is absolutely vital. It's often called VE.
What's that?
VE stands for the waiting time, or, more descriptively, the exposed to risk for individual I.
Exposed to risk. Sounds important.
It is. It's the actual amount of time that individual I was under observation and was at risk of the event happening, in this case, dying.
Why isn't it just the length of the study period?
Because people might enter the study late or leave early, or crucially, they might have the event, death, partway through. If someone dies halfway through a one-year study, their exposed to risk time is only half a year, not the full year.
Okay. So you're measuring the exact duration they were actually in the alive state and being watched.
Exactly. And this also connects to something called censoring. Sometimes the study just ends before the event happens for some people.
Like they're still alive when the observation stops.
Precisely. That's often called type I censoring, when the end date is fixed. Their observation is censored. We know they survived up to that point, but we don't know what happened after. Their V would be the duration up to the end of the study.
Got it. So you have N people, their outcome day, 0 or 1, and their exposure time, VET. Now what? How do you estimate OPE?
This is where a really powerful statistical technique comes in called maximum likelihood estimation, or MLE.
Okay, MLE. Sounds technical. What's the basic idea?
The core idea is actually quite intuitive, despite the fancy name. MLE is a method for estimating unknown parameters in a model like our force of mortality, VO.
How?
It asks what value of the parameter, in our case, would make the data we actually observed, the Dans and Vos, most likely to have happened. It finds the parameter value that maximizes the likelihood of seeing our specific data set.
So it's like finding the setting on the model that best explains what we saw in reality.
That's a great way to put it. Finding the best fit, the land that makes our observations seem most probable according to the model.
So, for our two-state Markov model, assuming that constant force of mortality, what does MLE tell us the best estimate for ρ is?
Here's the really elegant part. The maximum likelihood estimate for ρ, which we usually write as bear, with a little hat on top.
Yeah, okay.
It turns out to be incredibly simple and intuitive. It's just the total number of deaths observed across everyone in the study divided by the total exposed to risk time summed up across everyone.
Wait, really? Just total deaths divided by total time exposed?
Yep. So B hat XEV, where D is the total count of deaths, sum of all the Danes, and V is the total exposure time, sum of all the Vanes.
That's surprisingly straightforward. It's basically just the overall death rate you observed in your sample per unit of time.
Exactly. It directly measures the rate at which the event occurred within the total time the group was actually at risk.
Yeah.
Its power lies in that simplicity and directness.
And does this estimate, DV, have good statistical properties? Is it reliable?
It does. First, BRUTE is what we call an unbiased estimator, meaning that on average, if you were to repeat this kind of study many times, the average of all your MEHAT estimates would converge to the true underlying value of me. It doesn't systematically overestimate or underestimate.
That's good.
And there's more. As your sample size, the number of people N, or the total exposure V, gets larger, the distribution of this estimator, MEHAT, gets closer and closer to a normal distribution, the classic bell curve.
Ah, the normal distribution. Why is that useful?
Because we know a lot about the normal distribution, knowing MEHAT is approximately normal allows us to easily calculate things like confidence intervals, a range where we're pretty sure the true lies, and to perform hypothesis tests, like testing if mortality rate is significantly different from some expected value.
Can you give us a quick example to make that concrete?
Sure. Let's take that real dubious example mentioned in the materials. Imagine a scientist is observing 12,282 newborn wildebeest for their first year of life.
Okay, a lot of wildebeest.
Let's say, hypothetically, the true underlying force of mortality for these young wildebeest, the real bees, is 0.18 per year.
Right.
Now, the scientist observes them for a year and calculates their own MEHAT, DV, based on how many actually died, and the total wildebeest years of exposure, V. Because of random chance, their observed AHAT probably won't be exactly 0.18.
It'll vary a bit from sample to sample.
Exactly. But using the model and knowing MEHAT is approximately normal, we can calculate the probability of seeing certain outcomes. For instance, we could calculate the probability that the scientist observes a mortality rate that's higher than, say, 0.2, even though the true rate is 0.18.
So the model lets you predict the likelihood of observing different sample results.
Precisely. In that specific wildebeest case, the calculation shows the probability of the observed rate exceeding 0.2 is about 0.0532, or just over 5%. It connects the theoretical intensity to what you might practically observe.
That really clarifies how the estimation and its properties work. Now, you mentioned another model at the start, the Poisson model. How does that fit in? Is it a completely different approach?
It's a slightly different perspective, but remarkably, it often leads to very similar conclusions for estimating. Let's start with the Poisson distribution itself.
Okay, what is it?
The Poisson distribution is a fundamental tool in probability for counting events. Specifically, it counts how many times an event happens over a fixed period of time or space, assuming these events happen independently and with a known average rate.
Like the number of emails arriving in an hour or maybe typos on a page?
Those are classic examples, yes. Or, relevant here, the number of deaths occurring in a specific population group over a year.
And it has some unique properties.
One key property is that for a Poisson distribution, its mean, the average number of events, is equal to its variance, a measure of how spread out the counts are. That equality simplifies a lot of statistical analysis.
Okay, so how do we apply this Poisson thing to modeling mortality?
Well, here's what's really interesting. If we make a similar assumption as before, that the force of mortality is constant.
The constant sumption again.
Yes. If E is constant, and we look at the total exposure for a group, measured in person years, let's call this total exposure E, often written ERO for exposure at age X in cohort C.
Okay, total person years of risk.
Right. Then the actual number of deaths D observed in that group during that period can be modeled as a random variable following a Poisson distribution.
And what would the mean of that Poisson distribution be?
The mean would be the constant force of mortality multiplied by the total exposure E. So the expected number of deaths is E.
That makes intuitive sense. The average rate times the total time exposed gives the average count.
Exactly. The Poisson model provides a direct probabilistic framework for the count of deaths, given the exposure and the underlying rate E.
So if we use this model, the Poisson model, how do we estimate using maximum likelihood estimation? Do we get the same answer as the Markov approach?
This is the really cool part. Yes, you do. The maximum likelihood estimate for is under the Poisson model, EAT, is also just the total number of observed deaths, D divided by the total exposure.
So AT equals DE. It's the same formula.
It's the same fundamental calculation, deaths over exposure. It's incredibly neat how these two different ways of thinking of the process, one focusing on time to event, Markov, the other on counts, Poisson, lead to the very same intuitive estimator when AT is constant.
Wow. And does this Poisson-derived hat also have those nice properties like being unbiased and approximately normal?
Yes, it does. It's also unbiased, and its variance is calculated as 8 divided by the total exposure E. And again, for large amounts of exposure E, the distribution of AT approaches a normal distribution.
So statistically, they behave very similarly, too.
Very similarly in this common setup.
Let's use another example to see the Poisson model in action, maybe with confidence intervals this time.
Okay. Let's take the example from the material about a mortality investigation. Suppose over a 5-year period, they observed 46 deaths.
46 deaths.
And the total exposure calculated for the group under observation during that time was 7,500 person years. Using the Poisson model framework, the first step is the MLE for E hat is simply D divided by E. So 46 deaths divided by 7,500 person years.
Which is, let me see, about 0.000613.
Exactly, about 0.00613 per person per year. That's our best point estimate for the underlying force of mortality.
And because we know it's approximately normal, we can calculate a confidence interval.
Precisely. Using the properties of the normal distribution and the estimated variance, which would be E hat E, we can calculate, say, an approximate 95% confidence interval.
Giving us a range for the true.
Right. In this example, the calculation might give something like 0.000613 plus or minus 0.000076. So we'd be about 95% confident that the true force of mortality lies somewhere between roughly 0.000437 and 0.00789.
That shows how we move from just an estimate to expressing our statistical uncertainty around that estimate. Very useful.
Absolutely essential for making informed decisions based on the data.
Okay, so let's try and connect the dots here. We've looked at the Two-State Markov Model, focusing on time until an event, and the Poisson Model, focusing on the count of events in a given exposure. And despite coming from slightly different angles conceptually,
they land us in basically the same place for estimation, under that constant assumption.
Both point to the same fundamental maximum likelihood estimator for the force of mortality. A hat equals total deaths divided by total exposure time.
Exactly. That convergence is really powerful. It tells us this simple DV or DE calculation isn't just a random guess. It emerges naturally from these well-established probabilistic frameworks. It underscores its robustness.
So bringing it back to you, our listener, why should you care about these models? They might seem a bit mathematical, a bit abstract. What's the real-world relevance?
Oh, the relevance is huge, even if the models themselves operate behind the scenes. These aren't just academic exercises. They form the absolute bedrock for enormous areas. Think actuarial science, obviously.
Insurance premiums, pensions.
Right. But also public health modeling disease spread, understanding population trends, demography, risk assessment in finance and beyond. They are the fundamental tools that allow professionals in these fields to take raw data about events like births, deaths, sickness, recovery.
And turn it into actionable knowledge.
Precisely. They allow actuaries to set fair insurance premiums. They help epidemiologists predict how a disease might spread or how effective a vaccine campaign might be. They inform government policy on things like retirement ages or healthcare funding. They provide that essential foresight.
And how are these estimated values, the force of mortality estimates, actually used day-to-day by, say, an actuary?
Well, once they have estimates for maybe a single value, if assuming constant force, or perhaps a series of values for different ages, maybe smoothed out.
Okay.
They then plug these values back into those formulas we discussed, like TPX, XPADs, to calculate all sorts of other necessary probabilities.
Like the probability of surviving from age 65 to 85.
Exactly. Or the probability of dying within the next 10 years.
Yeah.
These probabilities, TPX and TQX for various X and T, are the direct inputs needed for pricing life insurance, valuing pension liabilities, creating life tables, and so much more. They are the statistical engine driving many financial and social planning systems.
Wow. So it really has been quite a deep dive then. We've navigated through what feels like the elegant simplicity of these two foundational models, the Two-State Markov and the Poisson. And we've seen how they give us this really solid framework for understanding and critically estimating transitions in life, especially mortality.
Hopefully you now have a much deeper feel for how these sort of abstract mathematical concepts get translated to real, practical, quantifiable insights. Insights that genuinely shape parts of our world.
Absolutely.
So maybe next time you hear a news report about life expectancy figures, or you see the risk associated with some activity quantified, you can appreciate how these quite sophisticated models, often stemming from just these two simple states, alive and dead, are working diligently behind the scenes to provide that crucial foresight.
That's a great takeaway. And maybe a final thought to leave you with. What other things in your daily life, maybe less dramatic than life and death, could potentially be viewed as a two-state process? On-off, working broken, subscribed, unsubscribed.
Yeah, interesting.
If you started thinking about the transitions between those states, the intensity of change, what surprising insights might you uncover just by applying this kind of modeling lens?